Friends, in this video, we shall try to understand the number of significant figures the results of these arithmetic operations must contain. But before that, let us refresh our understanding of significant figures. In this first example, we have a temperature of 300.12 Kelvin. Now from this measurement, we understand that we are 100% sure about the values of these 4 digits. But we are not 100% certain about the value of this last digit. If you are not 100% sure about the value of this last digit, then why are you reporting a value for this digit? That is because though I am not 100% sure about the value of this digit, I am reasonably confident that the value of this digit is a 2. I am 90% confident that its value is a 2. And that is useful information. That is why, though I am not 100% sure about the value of this digit, I am reporting it anyway, because it also contains some useful information. And all these digits that you are 100% sure of, and this digit that has some uncertainty, together are known as significant figures. So there are 5 significant figures in this measurement. And the next one is a weird one. Though there are 4 digits in this measurement, I am 100% confident about the value of only this digit. And I am reasonably confident about the value of the second digit from left. But I know nothing about the values of these 2 digits. These 2 zeros are here only to be able to express this length in centimeters. So, these 2 zeros do not provide any useful information. That is why these 2 zeros are not significant. So, in this measurement, there are only 2 significant digits, though there are 4 digits in total. And the next one is a simple one. There are 5 significant figures in this measurement. And in this measurement, there are 4 significant figures. Remember, trailing zeros in the decimal part of a measurement are all significant. That is, they came out of the measurement process. We made an effort to know the value of this digit and we found it to be a 0. Now, in the next measurement, by placing this decimal point at the end of this number, whoever recorded this measurement is telling us that this trailing 0 is significant. That is, this 0 came out of the measurement process. And this 2 is anyway a significant figure. So there are 2 significant figures in this measurement. And again, in this measurement, there are only 2 significant figures. Now, what is the significance of significant figures? See, in this temperature, there are 5 significant figures, and in this temperature, there are only 2 significant figures. So what is the difference between these 2 measurements? In this measurement, we know the temperature up to the second decimal place, that is the 100th place. Whereas in this case, we are able to measure the temperature only up to the 10th place. So, we know the temperature more precisely in this case than in this case. So this measurement is more precise than this measurement. So number of significant figures indicates the precision of the measurement. The more the number of significant figures, the higher the precision of the measurement. Now, there are 4 basic arithmetic operations: addition, subtraction, multiplication, and division. And we have to deal with multiplication and division separately from addition and subtraction. And let us deal with these 2 operations first. Say we have to multiply these 2 measurements, and when you multiply these 2, you would get 40.32. And each number present in a calculation is called a term. Here we are multiplying 2 terms, and the first term has 3 significant figures and the second 2 and the result 4. And this is a bit surprising. because number of significant figures indicates the precision of the measurement. The higher the number of significant figures, the higher the precision. So this calculation suggests that this result is more precise than both the terms that are multiplied with one another. And does it make sense to you? Do you expect to get a more precise result when you multiply two measurements? It does not make sense, right? So though this answer is mathematically correct, its precision is wrong. Now, if the precision of this result is wrong, then what should be the correct precision of this result? See, a chain may have many links, but it is only as strong as the weakest link. So the precision of the result is equal to or must be equal to the precision of the least precise term. Now between these two terms, this is less precise. So the precision of the result must be same as the precision of this term. So this result should have only two significant figures. And because the precision of the result depends on the precision of the term with least number of significant figures, it is called the limiting term. So the precision of the result is same as the precision of the limiting term. But in this result there are 4 significant figures, but it should contain only 2. Then what should we do? We have to round it. So we have to keep these 2 digits and drop these 2. Now the first digit that is getting dropped here is a 3, that is less than 5. That means you have to round it down. That means you have to simply drop these unwanted digits and leave the remaining number the same. So the answer to this is 40, right? No. If the answer is 40, that means there is only one significant digit and this trailing 0 is not significant. But our answer should have 2 significant figures. That means this 0 is also significant. To indicate that this trailing 0 is also significant, we have to put a decimal point at the end. So the correct answer for this calculation is 40 dot. Don't forget to put this dot at the end. Now this value has 2 significant figures. And in the next calculation, we have to multiply these 2 measurements. When you multiply these 2, you would get 5.22. Now this first term has 3 significant figures and the second 2, and in this result there are 3. But the limiting term has only 2 significant figures, so the result must also contain only 2 significant figures. So we have to round this result to 2 significant figures. That means we have to keep these 2 digits and drop this one. And the only digit that is getting dropped here is 2, that is less than 5, so we have to round it down. That means we have to simply drop this unwanted digit and leave the remaining number as it is. So the answer to this calculation is 5.2. And in the next calculation, we have to multiply these 2 measurements. When you multiply these 2, you would get 145.3 that has 4 significant figures. But this first term has 4 significant figures and the second term has only 1 significant figure. Remember, these trailing zeros are not significant. So the result should also contain only 1 significant figure because this is the limiting term. So we have to round this result to 1 significant figure. So we have to keep this digit and get rid of all the other digits. And the first digit that is getting dropped is a 4. You don't have to look at the remaining digits. And if it is less than 5, we have to round it down, right? So rounding down means dropping all the unwanted digits. If you drop all these digits, you will be left with 1. And does this answer make sense? When you multiply 1.453 with 100, do you get a 1? No, right? So in this case, instead of dropping these digits, you have to replace them with zeros. So if you replace all these 3 digits with zeros, then you would get 100.0. And this one again has 4 significant figures. But our answer should contain only one significant figure. So that means you have to completely drop this 0 and remove this decimal point and report the answer as 100. This has only one significant figure because these trailing zeros are not significant. And this answer is very interesting. When you multiply 1.453 with 100, you again got 100. But what do you get when you multiply the same 1.453 with 100 dot? Mathematically, you would get the same result, that is 145.3. But in this term, there are 4 significant figures and 3 in this. So this is the limiting term. So the result also must contain only 3 significant figures. So we have to round this result to 3 significant figures. Or we have to keep these 3 digits and drop this one. Now the only digit that is getting dropped here is a 3, that is less than 5. So we have to round it down. That means you simply have to drop these unwanted digits and leave the rest of the number the same. So the answer to this calculation is 145. You don't have to worry about the dot at the end. It has 3 significant figures whether there is a dot or not at the end. Now if you look at these two results, there is a big difference between them. To understand why there is a big difference between these two results, you have to understand the difference between these two measurements, 100 and 100 dot. Now in this measurement, there is only one significant figure. And if there is only one significant figure in a measurement, that is obviously the uncertain digit. So we are not even 100% sure about the value of this digit. This measurement means it is about 100. So going by the thumb rule for implied uncertainty, in this measurement, the implied uncertainty is plus or minus 100. That means the true value can be anywhere between 0 to 200. Look at this range of uncertainty. Whereas if the measurement is 100 dot, this dot indicates that these trailing zeros are also significant. So there are 3 significant figures here, and going by the thumb rule for implied uncertainty, in 100 dot, the implied uncertainty is plus or minus 1. So the true value could be anywhere between 99 and 101. Look at this range of uncertainty. So this is way more precise than this. That is why this result is more precise than this result. I hope that helps. Now in the next calculation, we have to multiply 3 measurements, 12.73 and 6.54 and 0.12. Obviously, we cannot multiply 3 terms at once. We have to first multiply any 2 out of these 3 terms, obtain a result, and multiply that result with the third term to get the final answer. So obviously, this is a multi-step calculation, not a single-step calculation. And it doesn't matter which 2 terms you pick first. Then let us multiply these 2 first. So when you multiply 6.54 with 0.12, you would get 0.7848. And in this calculation, the first term has 3 significant figures, the second 2, and this result has 4 significant figures. But it should have only 2 significant figures because the limiting term has only two significant figures. So we have to round this result. But remember, in a multi-step calculation, the results of intermediate steps should not be rounded. Only the final result should be rounded. So we have to use the entire unrounded intermediate result for calculation in the next step. So you have to multiply 12.73 with 0.7848, and when you multiply these two, you would get 9.990504. Now in this term there are four significant figures. Now in this intermediate result, how many significant figures are there? See, though we are using the entire result, this result should actually have only two significant figures. Therefore, we should consider only those significant figures this result would have if it were rounded, though we are using the entire result for calculation. So, in this term, there are only two significant figures, not four. So, to clearly indicate the number of significant figures in the intermediate result, we have to draw a bar on top of the significant digits. So, this has two significant figures and this four. So, obviously, this is the limiting term. So, the result also must contain only two significant figures. And this is the final result. So, we have to round it. We have to round it to two significant figures. That means we have to keep these two digits and drop all the remaining digits. And the first digit that is getting dropped is a 9. Don't worry about the remaining digits at all. Because it is greater than 5, you have to round it up. That means you have to add 1 to the last digit that is retained and drop these unwanted digits. That means you have to add 0.1 to 9.9. That is what we mean by adding 1 to this digit. 9 plus 1 is 10, and again 9 plus 1 is 10. So you would get 10.0. But 10.0 has three significant figures. But our answer must contain only two significant figures. So you have to drop this 0 and report the answer as 10 dot. Don't forget to put this dot. If you don't put this dot, then the answer would have only one significant figure. If you put this dot, that means this trailing 0 is also significant. So the answer then would have two significant figures. Now, in the next example, we are asked to convert 1.2 meters into centimeters. You know, by definition, 1 meter is equal to 100 centimeters. That means it is exactly 100. That is 100 with an infinite number of zeros after the decimal point. That means this has an infinite number of significant figures. This is an exact value. So to convert 1.2 meters into centimeters, we have to multiply this with 100. And remember, this 100 has an infinite number of significant figures. And this term has only two significant figures. So this is the limiting term. So the result also must contain only two significant figures. So the answer here is 120 centimeters. Remember, because we did not place the dot at the end, this 0 is not significant. So only these two are significant. So this is the correct answer. So this answer has the same number of significant figures as this term. That is why we said when you convert a measurement from one unit to another unit, the number of significant figures remain the same, or its precision remains the same. In the next example, we have to convert 27.3 feet into inches. Again, 1 foot is equal to 12 inches exactly by definition. That is 12 with an infinite number of zeros after the decimal place. So it has again an infinite number of significant figures. So this 12 has an infinite number of significant figures, whereas this term has 3 significant figures. So this is the limiting term, and when you multiply these two, you would get 327.6. But you have to round it to 3 significant figures, and you know how to do that rounding. And upon rounding, you would get 328. That is about multiplication. Then what about division? In this, we are asked to divide these two measurements. When you divide 128 with 11.6, you would get 11.0344828. And the term in the numerator has 3 significant figures, and the one in the denominator also has 3 significant figures. So it doesn't matter. The result also must contain only 3 significant figures. So we have to keep these 3 digits and drop the rest. So we have to round this result to 3 significant figures, and you know how to do rounding. So the answer to this calculation is 11.0. And in this calculation, we are asked to multiply these two and divide the result with this one. So again, this is a multi-step calculation. So don't round the results of the intermediate steps. First, let us multiply these two. When you multiply these two, you would get 13.684. You have to divide that with 2.795. See, in this term, there are 2 significant figures, and in this, there are 4. So this is the limiting term. So this intermediate result must contain only 2 significant figures. To indicate that, I have drawn a bar on top of these 2 digits. But I am using the entire unrounded result for calculation in the next step. So when you divide this with this, you would get 4.89588551. Now, how do we determine the limiting term in this calculation? In this term, there are 4 significant figures. Now, how many significant figures are there in this? Though there are 5 digits or 5 significant figures here, it actually should have only 2 significant figures. So you have to consider the significant figures this intermediate result would have if it were rounded to determine the limiting term in this calculation. Remember that. So this is the limiting term here. So the result must be rounded to 2 significant figures. And you know how to do rounding. I leave that to you. Now let us do one more multiplication before we move on to addition and subtraction. Let us multiply 0.02 with 0.0036. Upon multiplication, you would get 0.000072. Now do we need to round this result? Let us see. In this first term, there is only 1 significant figure. In this, there are 2. And in this result also, there are 2 significant figures. But there is only 1 significant figure in the limiting term. So the result also must contain only 1 significant figure. So we have to round it to 1 significant figure. So we have to keep this digit and drop it. And you know how to do rounding, and upon rounding, the result you would get is 0.00007. Now what did we just do in this rounding process? We removed the non-significant digits from the right end of this result. And if you look at this rounded result, you would understand that these zeros are also not significant, yet we left them there. Because we need these zeros to indicate the magnitude of this result. We cannot remove these zeros without changing the magnitude of this number. So we have to leave them there. So rounding is not about removing all the non-significant digits from the result. Then what is it about? It is about removing the non-significant digits from the right end of the number and thereby fixing the last significant digit in that result. And by fixing the last significant digit, we are fixing the precision of the result. So try to understand this. If you don't understand this, you might have some difficulty understanding addition and subtraction with measurements. Now let us do some additions and subtractions. In the first example, we have to add these three measurements, and when you add them, you would get 805. Now the question is, does this result have the correct precision, or do we have to round it based on the measurements that we added? Now if you think this result is correct, that means you are 100% confident about the values of these two digits, and you are also confident about the value of this last digit to a very high degree. So that means the implied uncertainty in this measurement is plus or minus 1. So you are saying that the actual measurement or the actual result is somewhere between 804 and 806. But let us see if that is correct or not. If you look at this first term, it has only one significant figure. If there is only one significant figure, obviously that is the doubtful digit. So we are not even 100% sure about the value of this digit. And we know nothing about the value of this digit. This digit could have any value between 0 and 9. If it is 0, then you would get one value here. And if it is 9, you would get a significantly different value here. That means the amount of uncertainty here is not this. It is not plus or minus 1. That means this last digit is not a significant digit. Then what about this digit? Now, if you look at these three digits, they are all significant. So that means this 0 is significant. So this is the last significant digit, and we don't care about the digits to its left, as I just explained. Rounding is about fixing the last significant digit. So this should be the last significant digit. So we have to get rid of this 5. So you have to round it, and for that you have to replace that 5 with a 0. Don't drop it. And if you say the answer here is 800, then it has only one significant digit. Here there are two significant digits. And if you put a dot at the end, that means there are three significant digits. So you cannot do that either. So to correctly indicate that there are two significant digits here, you have to put a bar on this last significant digit. This conveys that there are two significant digits, or you have to write it in scientific notation, 8.0 multiplied with 10 to the power of 2. See, once we understand the goal of rounding, it becomes easier. What is the goal of rounding? To find the last significant digit. When we add these three measurements, we get 385. Now the question is, does this result have the correct precision based on the three measurements that we are adding? Or is this 5 the last significant digit, or do we have to round it? It is easy to find this. All you have to do is write the terms that you are adding or subtracting vertically with their corresponding digits properly aligned. That is, all the ones must be in one column and all the tens must be in one column, and so on. Now start looking at each column starting with the rightmost column. Now in this column there are three digits, and all these three digits are significant. That means we can be confident about the value of this digit, right? So that means this is the last significant digit. Once you found the last significant digit, we don't care about the digits to its left. So this is the correct answer, and it requires no rounding. And I hope you find the next one easier. What do you get when you add these three? 8, 2, 5. Is it 528.1? Now, do we have to round it? For that, you have to start with the rightmost column. in this column, these two terms do not have any values, so we cannot be sure about the value of this digit, so this is not a significant digit. What about this column? In this column, there are 3 digits, and all the 3 digits are significant digits, so we can be sure about this digit to some degree. So this is the last significant digit, and we don't care about the digits that are to the left of the last significant digit. So this we have to keep, and we have to get rid of this digit, so we have to round it, and you know the rounding rules. When you round this, you get 528. Now what about this one? When you add these two, you get 4041. Again, do we have to round it? Start with the rightmost column. In this column, this term does not have any value, so we cannot be sure about the value of this digit, so this is not a significant digit. Whereas both the digits in this column are significant, so we can be certain about this digit to some extent, so this is the last significant digit. So we have to get rid of this digit, and you know the rounding rules, so upon rounding you get 14.0. Now what about this subtraction? When you subtract 12 from 30.79, you get 18.79. Now do we have to round this result? You know the drill. You have to start with the rightmost column. In the rightmost column, the second term does not have a digit, so we cannot be sure about the value of this digit at all. So this is not a significant digit. What about this column? Both the digits in this column are significant, so we are certain about the value of this digit to some extent. So this is the last significant digit, and once we found the last significant digit, we don't care about the rest of the digits to its left. So this is the last digit that we are keeping, and we have to get rid of this 9, so we have to round it, and upon rounding you get 18.8. You know how to do that. Now in this example, to be able to do this subtraction, we have to add 2 zeros here. Remember, these 2 zeros are not there in the original measurement. Now upon subtraction you get 96.88, right? Now do we have to round it? Remember, these 2 zeros are here only for the sake of subtraction. They are not there in the original measurement, so you have to remove them. Now start with the rightmost column. In the rightmost column, this term does not have a value, so we cannot be sure about the value of this digit in the result, so this is not a significant digit. And same here, this term does not have a value for this column, so this is also not a significant digit. Then what about this column? Both the digits in this column are significant, so we can be sure about the value of this digit to some extent. So this is the last significant digit. So this is the last digit we are keeping, and we have to get rid of these 2 digits. So you have to round it, and upon rounding, what do you get? Do you get 97? Now finally, as we discussed in another video, it is always a good idea to represent measurements in scientific notation. Using scientific notation, we can represent the number of significant figures without any confusion and without needing any convention like this. Now the question is, how do we perform arithmetic operations on measurements that are expressed in scientific notation? Here we have 2 measurements that are in scientific notation. How do we add them? This example is rather easy. In both the terms, this exponent term is the same. That is, these exponents are identical. They have the same value. So we can take out this common term and then simply add these significants to one another. And you know how to add these 2 numbers, right? So you have to write them vertically like this and add them first. Then look at the rightmost column. Here in this term, there is no significant digit in this column. Therefore, this digit is not significant. But if you look at this column, both the terms have significant digits, or all the digits in this column are significant. So this is a significant digit, and all the digits to its left are also significant. So we have to round this result to two significant digits. And you know the rounding rules, right? Here the digit that we are dropping is a 5. If it is a 5, whether to round up or down depends on the last digit that is retained. It is a 9, an odd number, so you have to round it up. So you have to add 1 to it. So it becomes 4.0. So the answer to this one is 4.0 times 10 to the power of 4. But the next example is not as straightforward because these exponent terms are not the same. These exponents do not have the same value. So you cannot simply add these significands to get the answer. Don't do that mistake. And there are two ways to perform this addition. One is to expand these terms and add those expanded numbers to one another. The other way is to somehow adjust these numbers so that these exponents become equal. Once the exponents are equal, we know how to add them. That's what we did here. Now let us try to do this addition the first way, that is by expanding these terms. See, the sign of this exponent tells the direction in which the decimal point must be moved, and the magnitude of this exponent tells the number of positions by which it must be moved. If there is a positive sign, that means you have to move the decimal point to the right. And if there is a negative sign, it means you have to move the decimal point to the left. So here 1.6 multiplied by 10 to the power of 2 gives 160. Similarly, 7.8 multiplied with 10 to the power of 3 gives 7800. You have to move the decimal point to the right by 3 places, 1, 2, 3. So you would get 7800. Then you know how to add these two numbers. And the other way to perform this addition is to make these exponents identical. You can make this 3 or you can make this 2. For me, this is easier. Let us make this exponent 2. Now I can write 10 to the power of 3 as 10 multiplied by 10 to the power of 2. Now if you multiply 7.8 with 10, you would get 78. So it is 78 multiplied with 10 to the power of 2 plus, I'm going to leave this as it is. So it will be 1.6 times 10 to the power of 2. Now these exponent terms are the same. So you can take that common factor out and add these significands, that is 1.6 plus 78. And you know how to perform this addition. Now what about multiplication? Multiplication is much easier. Here you have to simply multiply the significands with one another and the exponent terms with one another. So this can be written as 3.1 times 4.5 multiplied with 10 to the power of 4 times 10 to the power of minus 2. Now when the bases are the same in multiplication, you know you have to add the indices. You know the loss of indices, right? So this becomes 10 to the power of 4 plus minus 2. That is 10 to the power of 4 minus 2 or 10 to the power of 2. And you know how to multiply these two terms. So the answer will be 3.1 times 4.5 times 10 to the power of 2. I leave this calculation to you and the subsequent rounding as well. Now what about division? Same, you have to divide this significand with this one and this exponent term with this one. This can be written as 2.1 over 1.6 times 10 to the power of minus 6 over 10 to the power of minus 3. And during division, if the bases are the same, you know you have to subtract the indices. So it becomes 2.1 over 1.6 times 10 to the power of minus 6 minus of minus 3. So it becomes 2.1 over 1.6 times 10 to the power of minus 6 plus 3. That is 10 to the power of minus 3 times 2.1 over 1.6. You know how to perform this division and the subsequent rounding. So I leave this calculation to you.